What's up, guys? Mr. Patterson checking in with a video for IB Math SL. This is a video on section 23D, binomial distribution. This is actually the first of three videos that we're going to take going through this section here, binomial distributions, because it's a very big topic. We're going to really, in this first section, just talk about how to identify whether a discrete random variable is a binomial random variable or not. And then we'll begin to talk about finding probabilities, but from a more um, generic frame rather than the more specific frame that we're going to talk about as we get into the other sections. So first of all, what is required for a discrete random variable to be binomial? Well, there are four conditions for that. The first is that you must be able to classify your outcomes as either a success or a failure. So it doesn't mean that it only has two possible outcomes, but all of the outcomes can either be classified as successes or failures. So if I'm flipping a coin, I could say anytime I get a heads, that's a success. Anytime I get a tails, that's a failure. That's an easy one. If I'm shooting basketballs, if I make the basket, that counts as a success, and if I miss it, that counts as a failure. If I'm rolling a die, there's six outcomes, but if I say I only want to get a six, that means getting a six would be a success, and one, two, three, four, five would all be failures. So if you can classify them as success or failures, that's the first condition required for a binomial distribution. The next is that if we repeat this experiment in a number of independent trials, okay, so that means the trials have to be independent. So that means flipping a coin, rolling a die, picking names out of a hat, as long as I replace those names into the hat. Those kinds of things are going to be independent. Then we have to have the probability of success, which we're going to call P, has to be constant. We have to have a constant probability of success. It goes along with the idea of independent trials, but sometimes we need to kind of put that in there as a little extra caveat there. And then finally, we have a fixed number of observations. If we have a fixed number of observations, I'm going to flip the coin 10 times. I'm going to shoot 20 free throws, whatever the case might be. I know the number that I'm doing of that observation. And then if all of that is true, then we say that random variable x is a binomial random variable. So if x is the number of free throws made when I shoot 20, then x is binomial. All right. So let's look at this quick example looking at this spinner here on the right. It's a square spinner, and three of the four values on this spinner are blue, and one of them is white. So clearly we can see that the probability of finishing on blue is 3/4, and the probability of landing on white is 1/4. We would say that a success is a blue and a failure is a white. Now, if we look at this here, do we have a binomial setting? Well, what do we say? We said that we must have success and failure. Well, success is blue, failure is white. We said they have to be independent. Well, spinning this spinner here, the one spin has no impact on the next spin, so they are independent. In this particular situation, we're going to spin that three times, so therefore we do have a fixed number of observations, and that probability of success is always going to be 3/4. So let's just first define the random variable. So x, the random variable x, is going to be the number of successes or the number of blue outcomes out of 3. So that means x can take the values 0, 1, 2, or 3. I could have all of them white, one of them blue, two of them blue, or all three of them be blue. So there's four different values that x can take. Now the next thing we want to think about is, well, how do we find the probabilities of each one of those outcomes? And if we see here this kind of complex tree diagram with three different levels for three different spins, we could start to see how we can find these probabilities. And this is the part where I'm saying, right now we're speaking a little bit more generally about how to find these probabilities, whereas in the next couple of videos, we're going to see how to find these probabilities a little bit more easily. But we're right now putting it into the context of what we already know. So if I'm looking for the probability that x equals 0, that means none of them are blue, they're all white. Okay, so that's going to be a quarter times a quarter times a quarter, or a quarter cubed. That's 1/64. If I'm talking about where x equals 1, that means I have one blue and two white. Well, maybe I go blue, white, white. Maybe I go white, blue, white. Or maybe I go white, white, blue. So you see how there's three scenarios. That's why you see there's these three check marks here. So what we're going to do is we're going to take that 3/4, which is the probability of getting one blue, times 1/4 squared because we have 2 whites, but then we're going to multiply by 3 because there's 3 different ways that that could happen. So we can multiply all that out to figure out what the probability of getting x equals 1. X equals 2 is very similar, except instead of 3/4 times 1/4 squared, it's 3/4 squared because it's 2 blues times 1/4. Still times the 3 though, because there are 3 ways to get 2 blues. And then if x equals 3, there's only one way it can happen. Go blue, 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 3/4 to the third. So that way we can have all of the probabilities for those x values. Now, when we look at those there, if we added all these up, this is me just kind of explaining or showing how we're going to expand all these. If we add all these up, we should end up getting 1 because we've accounted for all possible values there. All right. And if we make this spike diagram here, we can see the probabilities of each one of them. So it's the lowest at x equals 0, and then the next highest when x equals 1. And the probability that x equals 2 and 3 happen to be the same here. Not always going to be the case. It just happens to be the case in this particular scenario here. Now, if we look at this, it should make sense that the probability that x equals 0 and 1 is lower than the probability that x equals 2 and 3 because it's more likely to be a blue than it is to be a white. So for that reason, we're going to have higher probabilities on the high side. But if the probability of success were lower, then we'd have a higher probability on the low side. Just kind of common sense there. All right. Now, we can then start to put this in more generic form by saying the probability that x equals x is 3 choose x, right? This is not a fraction. This is 3 choose x, which we can use the NCR function on our calculator to find that number. Basically, that number is going to be the number of times or the number of ways we can get x successes in 3 trials. Then it's going to be 3/4 to the x because it's the probability of success to the number of successes. And then it's 1/4 to the 3 minus x, the probability of failure to the number of failures. Because if you have x successes, then that means you have 3 minus x failures. So we could put it into this statement here, 1/4 cubed plus 3 times 1/4 squared times 3/4, etc., etc. And again, we can understand that that's all going to be 1. Now, if you look at this here, look at the coefficients. It's 1 here, even though we don't write it. Coefficient is 3 here. Coefficient is 3 here. Coefficient is 1 here. Those are the same as the binomial coefficients that we can find using binomial expansion. They come from Pascal's triangle, which we've certainly seen before when we did our binomial expansion. So that means that these values here can be found just by doing the binomial expansion of 1/4 plus 3/4 cubed. And we'll see that as we move forward. If we were to take a look at this example here, it says, first of all, expand 9/10 plus 1/10 to the 5th. Well, if I go to expand that, I would go down to the 5th row of Pascal's triangle, and I would see the first coefficient is 1, the next coefficient is 5, and then it's 10, and then it's 10, and then it's 5, and then it's 1. If you're a little unsure about that, go back through your notes about Pascal's triangle, or just go to a YouTube video about Pascal's triangle to help you understand how to find those coefficients there. All right, once we have that, notice what happens here. The first term, 9/10, we have 9/10 to the 5th. The second term is 9/10 to the 4th, 9/10 to the 3rd, etc., etc. And the last term has no 9/10. It's really 9/10 to the 0 power, but there's no need to write that. Now, why is that happening? Why do we start at 5? Well, it starts out as 5 because we're starting off here with the idea of having 5 successes, then 4 successes, 3, 2, 1, and 0 successes. And this 1/10 here, this is the probability of failure. So if I have 5 successes in the first one, I have no failures. That's why I have no 1/10 here. Again, it's really 1/10 to the 0, but I don't have to write it. And then I have times 1/10 to the first, 1/10 to the second, to the third, to the fourth, and to the fifth. And this gives me each expression for the number of successes. So if I'm talking about 5 successes, it's just this first part here. This one here is 4 successes, 3 successes, 2, 1, and no successes here. So we can then use these probabilities to answer the question. All right, and we're going to see this on the next slide as well. We're going to take a look at, in this scenario, oops, sorry about that, an archer has 90% chance of hitting a target. So that's why we have this 9/10 here. And it says, therefore, if you have a 10% chance of not hitting the target. So if we fire 5 targets, firing the 5 targets gives us this exponent of 5 up here. If we're looking for twice only, well, let's go through it. This is 5 successes, 4, 3, 2. So 2 only can be found just by expanding and simplifying or evaluating this term here. At most 3 means I'm going to include this part plus this part plus this part plus this part. And you can see it in this example right here. You're just taking those values here. So hits twice is going to be this part of the expression right here. So that's going to be about 0.0081. Hits at most 3 is the same thing as saying x is less than or equal to 3. Well, less than or equal to 3 is equal to 0 plus 1 plus 2 plus 3. So you add up all of those instances and you get 0.0815. Instead of finding at most 3, I could have also done 1 minus the probability of 4 and 5. Add those two together. Sometimes it's a little easier to do it that way. That's it for this first section here. I'd like you guys to work on the practice on page 621, numbers 1 through 5. In some of these, you're going to be identifying whether the random variable is binomial or not. In other ones, you're going to be finding probabilities for those binomial random variables. Let me know if you're having any trouble with that, and we'll get back together soon. Take care, guys.